In this video, we're going to do some practice problems with angular motion. One thing we want to get really good at is being able to convert from the number of radians that we've moved to a number of rotations or a linear displacement. So in this problem, we've just got a hoop, just some kind of circle, moving with an angular velocity of 6 radians per second and decelerating at 0.5 radians per second squared. What we want to know is, how long does it take to come to a stop? How many radians does it travel? How many rotations does it make? And how far does it travel linearly? So first off, let's make a variable list, just like we would for linear kinematics. And then to this variable list, let's add the other things we're looking for. We're also wondering about number of rotations, so let's put rotations. And then we're wondering about the linear displacement. Now let's remember, linear displacement versus angular displacement. That's just going to be theta times the radius of the circle. So we're going to need to know a radius. And so let's give our hoop a radius. Let's say 2 meters, just for simplicity. So let's fill in our variable list. Our initial, let's give that initial, our omega naught is 6 radians per second. Our angular acceleration is going to be 0.5 radians per second squared. And we're wondering about time. And so our final velocity is going to be 0, of course, because we're going to slow down until we come to a rest. And so we can use classic kinematic equations. And then plug in our variables. We're going to get to 0, so that's going to be 6 plus negative 0.5 times t. And with just a little bit of algebra, we can see that we get 12 seconds for our time. And now we want to know, how many radians are we traveling? Well, that shouldn't be too tough. We can use our normal displacement equation to solve that. We can plug in our variables to that. We're going to start at an angular displacement of 0, simple enough, and then our initial velocity is 6 times our time of 12 plus 1/2 times negative 0.5 times 12 squared. And if we run that calculation, we end up with an angular displacement of 36 radians. So let's write that in here, 36 radians. Now, how far would that be linearly? Well, we can just take 36 times our radius of 2. 36 times 2 is 72 meters. And so it's as simple as that. We just take whatever our angular value is multiplied by the radius. So the last thing we want to find is the number of rotations. Now, rotations is very straightforward to find. It just requires us to remember that there are a specific number of radians in each rotation. So to go around this circle one time, I'm going to go 2 pi radians. And so if I have a number of radians, I just take my theta divided by 2 pi. That will give me my rotations. Nice and simple. So I'm just going to take my 36 radians that I traveled, 36, divided by 2 pi, and that will give me my number of rotations. When I calculate that, I get 5.73. So I get 5.73 rotations. There we go. We found everything. Let's set up another one. All right, in this problem, I have a motor set up. And this motor is going to turn on, so it starts from rest, and it turns on, and it's going to accelerate at 1.2 radians per second squared, and then it's going to travel for 200 radians. I want to know, what is my angular velocity after it's traveled 200 radians? Then after that, I want to know, how many rotations has it gone through, And what are its rotations per minute, also known as RPM? This is going to be a very common measurement for rotational velocity. It's not very easy to use in mathematics, but it is really easy to visualize and consider. And so in real life, when you see ratings for how fast something is going to move, maybe it's an electric motor, maybe it's an internal combustion engine, you're often going to see these ratings in RPM. So it's useful to be able to figure out how to go from an angular velocity to rotations per minute. So we'll look at that as well. So first off, we want to find that final rotations, that final angular velocity. And to do that, we're going to set up our combined equation. All right, so I'm looking for my final angular velocity. I've got an initial, which is going to be 0, so we can get rid of that, plus 2 times 1.2 for my angular acceleration, times my 200 radians that I travel while I'm speeding up. And when I do that, I get 480 radians per second. Let's write that in, 480 radians per second. And then I want to get my rotations, my number of rotations. Well, to do that, once again, I'm going to remember there are 2 pi radians in each rotation. So I'm going to convert by dividing by 2 pi radians. It's going to give me my number of rotations. Another way I can set that up is I can say I've got radians, and I want to go to rotations. And I know that in each rotation there are 2 pi radians. So just do our dimensional analysis, just like we did in chemistry. And so I would divide by 2 pi in order to get my number of rotations. So we've got 200 divided by 2 pi. And for our number of rotations, we get 31.8. And now RPM. I'm going to use dimensional analysis to figure this out. I've got 480 radians per second. I want to go from radians to rotations. Well, conveniently, that's going to be the same thing I do here. So let's do that same thing. I'm going to go from radians to rotations, getting rid of my radians, and there's 2 pi radians in one rotation. And then I want to go from seconds to minutes. So seconds to minutes, how many seconds are in a minute? 60 and 1. So I take 480 times 60 divided by 2 pi. And when I do that, I get 4,584 rotations per minute. There we go. So we're able to make these conversions just by looking at our units a little more specifically, using these same techniques that we've used in the past. Now we're not going to do anything too complex in this unit with angular motion. We're mostly just going to be moving back and forth between these and being able to identify number of rotations and converting these into their linear counterparts. So go ahead and practice these. Take a look at the answer key if you need help, and then we'll move on to satellite motion.